Today we are going to find the derivative of tan x using the definition of the derivative. So let's start. So our function is tan x. Uh, so I'm letting y is equal to tan x, and y is a function of x, as you can see. And the definition of derivative is, we call the derivative of a function dy by dx or f dash of x, whatever. You can use any of those. So dy by dx is equal to limit h approaches 0 of f of x plus h minus f of x over h. So f of x here is tan x. So for finding f of x plus h, we just need to replace x with x plus h. So this will become tan of x plus h minus f of x is simply tan x divided by h. And we are finding the limit of this expression. We are trying to find what this expression approach, what value does this expression approach when h is approaching 0 in this expression. So what can we do to find this limit? Right now, if you put h is equal to 0 in this expression, you will get 0 by 0 form, which doesn't help us. So we need to write it in a form which we can use to find this limit. So we can write tan as, so I basically didn't know the formula for tan of x plus h if it exists. So I've written this tan in the form of sine over cos. So tan of x plus h is sine of x plus h over cos of x plus h, minus tan is simply sine x over cos x. So sine of x plus h, meaning sine of alpha plus beta, we have a formula for that. Cos of alpha plus beta, we also have a formula for that. So sine of alpha plus beta is simply sine alpha cos beta plus cos alpha sine beta. So here alpha is x and beta is h. So this will be sine x cos h plus cos x sine h over cos of alpha plus beta is cos alpha cos beta minus sine alpha sine beta. So alpha is x and beta is h. So we'll just replace alpha and beta with x and h. Minus sine x over cos x will remain same over h. So the main problem here is this h, which is written in the denominator. So we need to get rid of it. Firstly, in the numerator, we can take the LCM. So the LCM will be cos x into cos x cos h minus sin x sin h. And when we take the LCM in the numerator, we'll get cos x sin x cos h, because we need to multiply the numerator of the first fraction with cos x, because that is what is missing from its denominator, minus sin x will be multiplied with cos x cos h minus sin x sin h. So because this factor was missing from its denominator, which was simply cos x. So if we multiply sin x with these two terms, cos x cos h minus sin x sin h, we get minus sin x cos h plus sin square x sin h. So if we look at the terms, the first and the third term, they are basically the same with opposite signs, so they'll get cancelled. So the remaining remains the same. So we'll have cos square x sin h term plus sin square x sin h term over cos x times cos x cos h minus sin x sin h, and this whole fraction is being divided by h. So in the numerator of the fraction written in the numerator of this whole fraction, sin h is common, so we can take sin h common, and we'll be left with cos square x plus sin square x, which is simply 1 over the same denominator divided by h. So we get limit h approaches 0 of sin h, because cos square x plus sin square x was simply 1, so 1 times sin h is sin h, over cos x into cos x cos h minus sin x sin h over h. So this h, this can be, if we want to, this whole fraction is being divided by h right now, so if we want to multiply it with the denominator gets inverted, so the denominator was h over 1, so now it will become 1 over h. So why are we doing this? Because we want to get rid of this h, and this will help us in doing that. So this will become sin h over cos x into cos x cos h minus sin x sin h into 1 over h. So if we look at this expression, we can use the limit, which is a very well known limit, sin h over h. So we can shuffle the denominators. So I've written this as sin h over h into 1 over cos x cos h cos x minus sin x sin h. So there's a property of limits that if you are taking a limit of a product of two expressions, you can, it is basically equal to the product of the limits of those functions separately. So this will become limit h approaches 0 of sin h over h into limit h approaches 0 of 1 over cos x cos x cos h minus sin x sin h. So the first limit is basically equal to 1, and I have proved this in another video, that when the variable approaches 0, sine of that variable divided by that variable is simply approaches 1. So this will be equal to 1 multiplied by, if you look at this limit, if we put h is equal to 0 in this, we can do that, because we don't get a 0 in the denominator, and we can't get 0 by 0 here, because in the numerator we have 1. So this will become 1 into 1 over cos x into, so h is approaching 0, so we can put h is equal to 0 in this expression, because h is equal to 0 is not making this undefined. So we can put h is equal to 0 in place of, put h is equal to 0, but obviously the functions involving x will remain same. So this will become 1 into 1 over cos x into cos x cos 0 minus sin x sin 0. So this will become 1 into 1 over cos x times cos x, cos of 0 is 1, minus sin x, and sin of 0 is 0. This is equal to 1 into 1 over cos x into 1 is cos x, minus sin x into 0 is 0. So we're left with 1 into 1 over cos x times cos x minus 0, which is cos x. So this is equal to 1 into 1 over cos square x, and 1 over cos square x is simply secant square x, because the reciprocal of cos is simply secant, and here we have a square, cos square, so this will become a secant square. So this is equal to 1 into secant square x, and finally we get our answer, the derivative of tan x, which is simply secant square x. And this result basically is true when x is in radians, because we have used a limit, this limit, sin h over h, when h approaches 0. So for this limit to be true, or this limit to be equal to 1, we must have h, or the variable, basically in radians. So this has to be in radians, and h needs to be in radians here, and if we are using this limit, our original angle, which was x, that also needs to be in radians, because this result holds when h is in radians.